This time, we will now explore the phenomenon of diffraction. So diffraction is actually a consequence of Huygens-Fresnel Principle. By the way, I'll just pronounce this as Huygen, though the Dutch pronunciation of this is difficult. Huygen, so I'll just pronounce this as Huygen. So diffraction is just a consequence of Huygen-Fresnel principle, wherein if you have, for example, a point source, and this point source produces a wave. So these waves is actually a source of secondary wavelets, and each point of this wave acts as a point source and it produces secondary wavelets. And the superposition of these secondary wavelets will actually result to the primary wave that is produced by this point source. So essentially, when we talk about interference, it's actually the superposition of individual sources of light wave. But unlike diffraction, you were talking about the same wave, but this time, it's the one that produces this diffraction pattern. So for example, you have this opaque screen, but there's a slit in the middle, and the width of this slit is D. Remember from our study of interference, we use capital D as the distance between the slit and the screen. But this time, we use capital D to represent the width of the slit. If we illuminate this with a coherent wave, there will be a resulting diffraction pattern on this screen, and it looks like this. To derive an expression for the diffraction pattern caused by a monochromatic light that passes through a slit with width D, let's consider various scenarios. So for example, if the light rays directly enters the slit at a zero angle, then what we observe is actually a pure zeroth order maxima, or the central bright maxima. When the angle of the light ray is 0, we will be able to observe a bright region on the screen. However, if we tilt the light rays at an angle theta with respect to its original horizontal direction, notice that we could still retain this light ray that is literally beside the edges of the aperture or the opening. And let's just represent this bunch of light rays with an average light ray like this. And then notice that when this third light ray has a path difference of lambda with respect to this ray, so by symmetry, then the middle ray will have a path difference of lambda over 2. Now, when these two rays reaches the screen, since they have a path difference of lambda over 2, then this will result to a destructive interference. And when these two light rays, this one and this one, reaches the screen and they interfere, this would also result to a destructive interference. But notice that if this ray and this ray interfere with each other, they will result to a constructive interference. So it's actually two pairs of light ray versus one pair. So what you will actually observe is less bright region or a dark region on the screen. So this time, what if we change the angle in such a way this last ray here has a path difference of 3 lambda over 2 with respect to ray 1. And by symmetry, some of the rays has a path difference of lambda and some of the rays has a path difference of lambda over 2. Now, if you try to do some visual inspection of this, there are more pairs of light rays that will result to a constructive interference than destructive interference. Hence, this will result to a bright region in the diffraction pattern. So let's focus our attention to this relationship. It seems that this is the expression or condition to produce a destructive interference in a diffraction pattern. And to generalize this, if we have a path difference of Dsin theta and it is equal to integer multiple of the wavelength of the light, then this will result to a destructive interference. Notice that here m equals an integer multiple, but we should exclude 0. So m here is actually equal to negative positive 1, negative positive 2, negative positive 3, and so on. So again, this is diffraction. Diffraction is the bending of a wave around the edges of an aperture or the spreading of a wave around obstacle. So if we have an aperture or an opening like this, if we have a parallel plane wave and it reaches this opening, then after passing through this slit, it will diffract or spread out through space. And for example, if we have an edge like this and you have a point source here and it produces a wave, so the wave actually bend around or spread around the edge. So diffraction again is a consequence of Huygens-Fresnel Principle. For example, if you have a plane wave that passes through this slit, each point of that plane wave will be a source of secondary wavelets. So for example, I'll focus on this wave source alone. Its adjacent point is also a source of secondary wavelets and so on until it reaches the final point. When these secondary wavelets superimpose with one another or they undergo interference with one another, they will result to a diffraction pattern like this. What if we have a double slit? So what would its diffraction pattern look like? We have this observation that if there are two slits of width d, so each has a width d separated by a distance small d. We could just measure this d by locating the center of each slit and then measure the distance between them as small d. The diffraction pattern is the interference pattern of 2-point sources separated by d multiplied by the diffraction pattern of a single slit with width d. So for example, this is the screen. If we have two slits, remember that when we discuss interference, the slit is almost like a point. We have this kind of slit with a very small slit width, not actually equal to d, but it's almost like a point. Then their interference pattern looks like this. Next, recall our pattern for a single slit diffraction. If I try to plot the intensity profile of this pattern, we have this very bright zeroth order maxima and then a less bright first order maxima and then secondary order maxima until the amplitude goes to zero. So the same goes here. So imagine if we multiply this to this pattern. Let me rotate this figure and it looks like this. So again, we have an interference pattern and a diffraction pattern, and their product, if you multiply these two waves together, it looks like this. So in a way, when you have double slit diffraction, its intensity pattern looks like this. When you have a double slit diffraction, it has a very bright region and first order maxima and then second order maxima and so on. If you want to measure the distance between two maxima, it's a little bit difficult to measure the distance between them because as you move away from the zeroth order maxima, this region here becomes spread out and at the same time it loses its brightness, so it's a bit hard to measure the distance between higher order maxima and even to distinguish them from the dark region because they easily die down. It seems that we are able to increase the brightness of the diffraction pattern by increasing the number of slits where our source passes through. So let me transfer this figure here. If we have two slits, the relative intensity of our diffraction pattern looks like this. But what if I try to increase the number of slits? So based on experiment, I'm able to enhance the brightness of the higher order maxima or the amplitude or the intensity of the higher order maxima when I increase the number of slits. So eventually, I'm able to create a diffraction pattern that is more pronounced or that is more distinct than just a system that consists of two slits. So if we increase the number of slits, we are able to enhance the higher order maxima of this diffraction pattern. So it almost looks like a clear line, and the spreading out of the bright region and the dark region becomes distinct. So in a way, we were able to enhance the diffraction pattern by creating a clear distinction between the bright region and the dark region. So in optics, we have a special term for this kind of optical element, and this is what we call diffraction grating. So usually you have an opaque object like this, and you try to just put very tiny slits, and this is actually what we call a diffraction grating. And diffraction gratings are usually described by the number of lines per unit length. So for example, you can buy a diffraction grating with 1000 lines per millimeter. So that means there are 1000 slits for every 1 millimeter of this diffraction grating. So apparently, it has wide applications. For example, you want to determine the wavelength of an electromagnetic wave that is being released by a molecule or a biomolecule, and you let it pass through a diffraction grating. And from this, you could determine other properties of that monochromatic wave emitted by an object and so on. So let's try to answer some problems. This problem is from OpenStax University Physics, Volume 3, Chapter 4, Diffraction, Problem 19. So here we are asked, how wide is a single slit that produces its first minimum for 633 nanometer light at an angle of 28.0 degrees? At what angle will the second minimum be? So for example, I have a single slit, and this is the screen. If this is the zeroth order maxima, and this is the first order maxima, then in between them would be my first minimum. For part A, how wide is the single slit? So again, the condition for destructive interference when you have a single slit diffraction is that if this slit has a width of d, then the path length difference, d sine theta, should be an integer multiple of the wavelength of light. And this m is equal to, if we're talking about destructive interference, it should begin with negative positive 1, negative positive 2, negative positive 3, and so on. So in the problem, the first minimum occurs at an angle of 28.0 degrees. So if this is the first minimum with respect to the center, so if I try to separate this triangle here, so again, this point is the first minimum, and this is the center of the diffraction pattern. So this is the theta between this first minimum and center of the diffraction pattern, and this theta is equal to 28.0 degrees based on the given. And since this is the first order minimum, m here is actually equal to 1. Our target variable is the width of the single slit, so I'll rewrite this in terms of d. D equals m lambda sine theta. M here is 1 because this is the first minimum, and lambda is 633 nanometers divided by sine 28.0 degrees, and I'll end up with d equals 1.35 times 10 raised to negative 6 meters. Now for part B, at what angle will the second minimum be? So for part B, the second minimum, if we look at this equation, it refers to m equals 2. So we already have a value for d. Here we have theta equals arc sine of m lambda over d. So m here is equal to 2, lambda is 633 nanometers, and d is 1.35 times 10 raised to negative 6 meters. Plugging in the values, we have theta equals 69.87 degrees. If you did not round off this value, then you'll have a different result here. This problem is from OpenStax University Physics Volume 3, Chapter 4, Diffraction, Problem 21. Find the wavelength of light that has its third minimum at an angle of 48.6 degrees when it falls on a single slit of width 3.00 micrometers. So again, if we have a single slit, and this is our screen. So our first order maxima, let's assume that it is at this point. The distance from the center of the slit towards the center of the zeroth order maxima is represented by this dashed line. The first order maxima, let's assume that it is at this point, and then the second order maxima is at this point, and the third order maxima is at this point. So in between, for example, this would be the first order minimum, this will be the second order minimum, and this will be the third order minimum, which is, according to this problem, this third order minimum is at an angle of 48.6. So if I try to separate this triangle, I have the third order minimum. So it is at an angle of theta equals 48.6 degrees with respect to the line connecting the center of the zeroth order maxima and the center of the slit. And the width of the slit is D. Based on the given, capital D is equal to 3.00 micrometers. So we are asked to find the wavelength. Recall that the condition for destructive interference is that the path difference should be equal to an integer multiple of the wavelength, where m here is equal to negative positive 1, negative positive 2, negative positive 3, because m equals 0 will actually result to a constructive interference. That's why m is limited to negative positive 1, negative positive 2, and so on. So our target variable here is the wavelength. So I'll rearrange this in terms of wavelength. Lambda equals m over d sine theta, plugging in the values. So according to the problem, this minimum is the third minimum, so m is actually equal to 3. D is the width, which is equal to 3.00 micrometers times sine of 48.6. Plugging in the values, the wavelength is equal to 750 nanometers. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!